Okay, so just before the break, we had started to look at power amplifiers. So we'll continue that today. And then we will also do a little bit of looking at cadence. Before we get into class, I did want to say that we were going to make a minor modification to the way we do the projects just to help some of you along, I think. And that will be that project 2 and 3 will be due at the same time. So I'll give you till the end of class to do them. Now, project 3 is just going to be laying out some portion of the design that you're working on, extracting it and adding that to the simulation, and then reporting on the differences between your layout and your schematic-based design, which is really the name of the game in RFIC. The layout that you do, even on a breadboard, is important, but in RFIC, it's particularly important. Okay, so we were looking at power amplifiers just before the break. And notably, we were really looking
so
at.
Professor, just to clarify, so the deadline for project 2 and 3 will be in the same date, and it would be almost the end of the semester. Is it correct?
Yes.
Okay, thank you so much.
That's correct.
So much.
There will be a small oral presentation portion of your project 3. So you'll have to do that portion before the end of the semester because we'll do that in class. Sure. The report part can happen afterwards, provided that I have enough time to not have the grading folks kill me.
Thank you, Professor.
They like to draw them and quarter them and send them to all areas of the drill field. Okay. That's what happens to bad professors. All right. And you were wondering why you didn't see Mr. Smith this semester. I don't know if there's a Professor Smith.
Once you have tenure, you've got that position for life.
That's right. That's right. And there is a way to get rid of you. Okay, so what we were primarily seeing with a power amplifier, with a Class A power amplifier in particular, was that we ultimately had to reduce the optimum termination impedance quite a bit in order to get any kind of power out of the device because we can't use high voltage swing. So essentially what we're doing is trading off voltage swing for current swing. If I have high current swing and moderate voltage swing, I can still get a good amount of output power. And we saw ultimately that this causes us all kinds of problems in terms of efficiency. So we're going to look at a few things to try and fix that today. So the first thing that we noted in terms of efficiency is that what's going on here? Okay, the first thing we noticed in terms of efficiency was that limiting the voltage swing caused us to have to use a very small R-opt and hence more current through the device. And increasing the current through the device lowers it requires a lower transistor impedance. Okay, well, that's not necessarily a problem. We can make the transistor as wide as we want to, really. That's one of the nice things about a MOS device. We can just keep increasing its width and drive more current through the device. And by the way, this is also true of other types of devices. So for instance, if you were using a bipolar transistor in an integrated circuit process, you can increase the emitter area of the device as well, and that will cause it to be able to handle more current. You know, really what we're talking about is making the current carrying dimension in the transistor, which arguably will be the width times the length product. We're making it bigger, and that allows it to handle higher current. Okay, so the name of the game here, though, is that we have, when we start making this device really big, what's happening to the output resistance of the device? It's decreasing. So our out of the device is decreasing. And we know that our matching network, this should be an output matching network, not an input matching network. The whole purpose of this thing is just to transform 50 ohms so that it presents, R opt to the device. This is not a physical resistor. This is just a matching network with a transform that's presenting R opt to the transistor. All right. So as we've already said, the more I, more W. More W reduced RO. And now let's see what happens here. So we have these two parallel resistors at the drain of the transistor. We have the one that we're presenting to the transistor and the parasitic. What happens there with respect to the transistor, the current source of the transistor? It's a current division, right? All right, so we can write this in terms of eta. We've got a current division. The current going into our load is little r naught divided by little r naught plus r opt. And we're working in terms of power, so we're going to square this ratio. And so our efficiency of our PA, if you'll recall when we were talking about the class A the other day, we had eta of the PA is equal to eta of the topology. So this is, class A, class AB, class B, class C. We haven't really talked about any of the other ones yet. We've only talked about class A, but we have the efficiency of our division, whatever it is. We have the efficiency of our matching network. So that output matching network also has some loss depending upon the size of the transform that it has to do. And remember, the bigger the transform we're making, the more loss that we're going to see in the matching network. And I'm not adding it here as necessarily part of the transmitting system, but technically we also do have to worry about the efficiency of the antenna. So this is, how efficiently the antenna couples signal to the air. And if I look at this, this is really, I shouldn't say the efficiency of the PA. This is really the efficiency of, the whole transmitter. Well, I'm not including other things. I'll say the PA for the time being. I'm not including things like the driver here. So I'll just say the PA. Okay, so what we immediately see is that we need to figure out how to increase R naught from the device. How do we make it bigger? So what are some things as a circuit designer that you can do to make R naught bigger?
Increase the channel length.
Yeah, that's right. What would that do to the performance of the device if I increase the channel length?
It will improve because of the reduced channel length modulation.
Well, it'll improve what metric of the performance?
Uniform current flow.
It will improve the linearity of the current of the device. Yeah, that's right. It'll improve gain. The output resistance will be higher, so it will improve gain. Anything else?
Yeah. And it will basically decrease the headroom. So
okay, it will decrease the headroom because VD-SAT is inversely proportional to W over L. Yeah, that's true. Anything like really really negative about increasing length?
Speed, low speed.
Yeah. What happens to the threshold voltage when I increase length?
Increase.
You should try that. I don't think that you'll find it increases the threshold voltage. Increasing length will decrease the threshold voltage. But the primary thing that will happen is that it will decrease the speed. So We can't really just increase length arbitrarily because the FT of the device is ultimately going to be slower. That means I'll be able to use it at a lower speed. All right, so increasing L does increase R naught, but I'm going to get, my mileage may vary on that one. What else can I do as a circuit designer? Well, we could do some type of power combining, but if you ask me, power combining is really just a form of doing an impedance transformation. I do power combining on chip with a transformer, a power combining transformer, and ultimately all that thing is doing an impedance transformation. So that's more or less the same trick that we're doing by decreasing our opt. Cascode. Okay. Now, you'll recall I've told you before, I believe in this class, that sometimes nowadays they call a cascoded transistor a stacked transistor. I believe that the people that do this, their interpretation is wrong. Cascode dates back to the vacuum tube era, and they didn't put a limit on the number of tubes that they stacked in principle. Now, in practice, tubes were expensive, so they didn't necessarily stack 10 transistors, but there was nothing really in the original work on cascodes that said that they couldn't. So I think a cascode and a stack are the same. I'll argue that until they draw and quarter me and send me out to the drill field. All right. So Cascode, what is Cascode? Like I just said, we're going to stack devices. We're going to distribute our voltage stress across two devices. So this has another positive benefit in that now I have two devices for VDS to swing across. So that's going to reduce the stress that each of the devices sees. I'm calling this big R naught now because it's the combination of the R naught of the stack device. What's the approximate resistance looking into the drain?
GM of the common gate transistor, RO, and then the common source transistor, RO.
Yeah, I think it's GM times RO squared. It's really RO times 1 plus GM times RO, but we approximate that as GM times RO squared. Yeah.
Doesn't limit the performance of circuit for high frequency when you have a stack?
Well, it not necessarily, and there are a couple of reasons for that. So one of the reasons is for that stack device, depending upon how I'm using it, it might be it might just be sitting in the triode region. It might not be doing anything other than sitting in the triode region. And even if it is an active device, oftentimes with the Cascode device, I'm going to reduce the size of the device because it's not really providing the transconductance, right? The transconductance is coming from the lower device. And so decreasing the size of the upper device will increase its resistance. So not necessarily going to affect speed that much. Bear in mind, I am adding parasitics, and anytime I add parasitics, I might have to tune the parasitics, a bit. So, more or less, the biggest problem here is I've got some parasitic capacitance that exists at this interstage node between the two devices, and that can reduce my gain because I have a path where signal at higher frequencies might want to leak through. Yeah. Also increase noise.
Is the top transistors
So I should be careful. I'm probably not going to use that device in triode for a linear amplifier. I'm going to do that if it's switching. So yeah, we have to be a little bit careful there. Okay, so Now there is a big drawback here. So, we just, ultimately said, okay, great, our opt increases. Our O increases, and now our opt can increase. And the reason is that I can make VDD, the supply voltage, bigger because I have two devices to distribute stress across. Okay, what happens to, is there anything negative other than the things we've already kind of talked about or touched on? The swing gets a little bit worse.
If you increase the VDD, like, is it really fair to say this gets worse? Like, if you're saying you increase the VDD, but yeah.
Well, this a very specific element of the swing gets worse. So what happens is I now have two devices that I need to keep saturated if I'm trying to keep these both operating as current sources. And so the knee voltage of this whole thing increases by quite a bit. So the swing is well, I take your point. I'll say, how about this? We don't really know what happens with the swing because we don't know what the optimum termination impedance is. So we shouldn't necessarily say that it's worse, but we do know that V knee is going to be bigger. So it's going to reduce the lower end of the swing range. So remember, V knee is the saturation voltage. That's the voltage level at which the device starts behaving like a current source. And now I have two devices. I need both of them to be current sources. So I need to have two V knees. V knee might not be equal for both devices if one of them is differently sized than the other device.
Yeah.
That's something that's been done. Yeah. It will inherently narrow band the circuit, but yeah, technically you could tune that capacitance out with an inductor. I don't generally think that it's worth it because the size of the inductor required to do that is typically quite big. And in fact, what more commonly is done instead of dealing with that capacitance, you've got the gate to drain capacitance due to overlap. So nowadays they just try and neutralize the gate to drain overlap and don't worry too much about whatever that parasitic is. Try and make it as small as possible by reducing the size of the cascoded device. All right, so how do we design a cascoded PA? Well, it's pretty straightforward. My output power is no different than it was before in terms of the equations here. So we can say that P out is equal to whatever V max is times whatever I max is. This is our P out. We'll just say saturated value. And for the sake of argument, we'll just say that V max, the maximum swing, will be equal to VDD minus 2 times V knee. These are all approximations. We're not going to come to any exact expression. We can use the simulator to do that later on if we want to. All right, and of course, we have VOV for the device is equal to 2 times I max over mu times C aux times W over L. This whole quantity square root. So this is just a expression for the overdrive voltage or VDSAT. You might have seen if you've had a past electronics course. And we sometimes call this voltage V knee. Okay, and then we also know what the max current is. So mu times C aux times W over L times VDD minus VTH squared. All right. All right, we're going to call this equation 2. We'll call this equation 3. Call this equation 1. So if we substitute 3 and 2 into 1, and we find the W over L that satisfies P out, we know how to size the power transistors in the stack. All right, now, as before, I'm making some, these are all approximations. This is not accounting for, all kinds of losses. But really, the principle here is the same as in any other analog course. You just kind of want to have a rough ballpark estimate of what you need of what the device size needs to be, and then you can go into the simulator and refine it. The model for the transistor is a lot more complicated than the model that we're using, our hybrid pi model, in order to make these calculations. And then we also know what our R-opt needs to be. Our R-opt to a first order is, V max over I max. Okay. All right, now in a practical sense, we can do this. We can run a DC simulation. We can find the GM for the devices. We can sweep the width and find GM as a function of width. We can do all kinds of things. I'll show you how to do that in just a moment. But what's almost always done with a transistor is, instead of doing this hand calculation, we're going to use what's called a load pull. Okay, now what does a load pull look like? Well, I take my power transistor. It might be a cascoded transistor like the one drawn here, and I put this variable electric length transmission line down. And then I might also use some variable capacitors and variable resistors at the load. And I'm going to start just sweeping. I'll change the load resistance. I might start at 50 ohms, and then I'm going to sweep the electric length. And then I'm going to change the load resistance to 60 ohms, and I'm going to sweep the electric length. And what it's going to do is allow me to present every possible combination of impedance to the drain of the transistor as I change the electric length of the transmission line. And in other words, I'm going to pull the load impedance across the full range of the Smith chart to determine what the performance of the device can be. Now, what we have in this picture is a load pull setup. And of course, I mentioned doing this at the output. You typically will do this at the input and the output. And as we pull those impedances at the input and the output, we're going to monitor P out, the power that the device is giving us. So we'll know what impedance corresponds to what output power. We're also going to monitor the efficiency, most likely just the drain efficiency here, because we're just doing this for a single device. And we're going to do this at all impedances. Now, if you've seen one of these setups, this is a load pull setup. So there's an active tuner at the input and the output. In the old days, we actually just had a variable length transmission line that they called a trombone. It was almost exactly like the slide on a trombone. You just kind of stretched it, and you were able to change the electric length of that transmission line. The active load pull systems are nicer. They're also a lot more expensive. So we don't have one here. but most of the power amplifiers I do are switching amplifiers, so I don't need them. So as you monitor, this, of course, I said we're probably going to monitor ADA, but maybe they're going to monitor PAE. You can see in this picture what goes on the load pole. That's exactly what they did. The peak PAE happens for some, value of impedance right there. The peak value of the power delivered happens for some impedance right there. They don't always, in fact, they probably almost never line up exactly. So you normally have to maybe trade efficiency for output power. There are some things that you can do with the geometry of the device in order to make that a more favorable trade. But here you can see it in this particular case that they're pretty close. The power delivered impedance and the power added efficiency impedance are not too far apart. Okay, and what each of these contours is some change in the PAE relative to the PAE max. So this, center point is PAE max. This is P out saturated max. And then every one of these contours represents some trade-off that I've made. So as I move away from that maximum point, I'm going to reduce the efficiency and I'm going to reduce the output power on those contours. But anywhere that if I present any impedance on this contour to the transistor, it will produce the same amount of output power. So it's a constant output power contour.
Does the smallest circle represent maximum efficiency?
Well, the smallest circle would just be a dot. So it's a point that would represent the maximum efficiency. It's almost never a locus of points for where the maximum occurs. I can't think of a case where it would be.
Okay, thank you.
All right, so we can do this in simulation. So we can basically take a power transistor, and I'm going to upload another of the Cadence tutorials. I uploaded the one on LNAs. I'm going to upload the one on PAs, and you can try some of those tutorials. And they have a virtual load pole that you can do for your device in the schematic. And it's much easier than having to play around with a trombone or with one of the electric load pole systems. Basically, you just tell it the range of impedances that you want it to swing through and the range of theta that you want it to rotate around, and it will virtually do that. So for instance, we start off in our system, we measure the output power efficiency gain at 50 ohms. So this would be at 50 ohms. And then now if I'm right at 50 ohms and I have a 50 ohm transmission line, what are the locuses of impedances I'm going to be able to present to the transistor? They're all going to be 50 ohms, right? So I don't really need to sweep around there. I could if it's easier. But the big thing is, okay, on the next one, I'm going to come along and I'm going to change this to 60 ohms, and I'm going to sweep the transmission line. So in this first case, no matter what I did, I presented 50 ohms to the device. In this next case, I'm going to present some ZL prime. So I'm going to start maybe right here, and I'm just going to rotate around, presenting all of these different impedances to the transistor and measuring the output power, efficiency, whatnot, gain of the device. And I can keep doing this for different loads. I can go less than 50 if I want, and every point that I sweep, I'm going to measure P out gain, PAE, or grain efficiency. And in the end, I'm going to get some contours, from the device. As I do this, I'm probably going to find, for most devices, that the optimum impedance is going to be a lower impedance for most CMOS transistors. I still, no matter what, even if I increase the resistance of the devices quite a bit, I'm still dealing with a smaller voltage than I am with 3.5 devices. So my point's going to be over here. I might have my, so this might be my, PA, P out max. And then I'm going to have contours that are going to do something like that. And of course, over here, I might find, who knows, different transistors do different things, but I'm going to find, this might be my eta max. And then when I go to design a power amplifier, I make some trade-off. I say, well, I really need output power from this one, so I'm going to sacrifice efficiency to get output power. Or my power spec is not that bad, so I'm going to, I might work over here and that'll give me a higher efficiency. So this is just, some type of trade-off. Of course, I might also have a gain spec that I have to meet. Yeah. Okay. Now, like I say, for integrated circuits, the nice thing that we can do nowadays is we can just do a virtual load pull. So you can change the size of your device and you can rerun a sweep of the load pull, see if the device is going to be able to meet your power specification. If it is, great, you're done designing your device. You can start designing the rest of the circuit. If it is not, then you iterate, make the device wider, Cascode, stack another device, whatever you have to do in order to get more output power. All right, so this is just kind of a repeat of what I was saying, before, from the data, we're going to map the output power, efficiency, gain for every value of RL, and we're going to get contours of P out, gain, efficiency, and those don't always line up. Ideally, they're close to one another, though. Yeah.
So for every example you showed so far there in the top half of the chart, is that because it's usually dominating the capacitance?
Well, what I would say is that normally the device looks capacitive, and so you need to present some type of inductive termination to resonate out that capacitance. That's most of the time going to be the case. I'm sure that there's some case where it isn't. But for instance, if the device has a lot of parasitic inductance due to bonding wires or something like that. Now, for our devices that we're going to be doing load pulls for, they're just going to look capacitive because you're not going to have, unless you add the bond wire inductance to the simulation, it's not going to be there. Yeah. Okay. So the biggest thing, in terms of how do I know when my design's done, okay, let's think at a high level engineering thought here. What is the benefit of having more output power from a system in a radio system? Yeah, I closed the link at a longer distance. PTX goes up, and so my power available at a receiving antenna is going to increase proportionally. Yeah, so that's good. What are the drawbacks of doing that, of increasing power? Yeah, normally I probably have to trade off some linearity as well. We didn't really talk about that, but that's definitely going to happen. I think the bigger thing is that there's almost always an FCC limitation. So the drawback is that you go to jail, or worse, in America, you get fined. Money is equivalent to imprisonment here, right? That's not a value statement. I'm just What about efficiency? What does efficiency do for us? Why do we want to
Efficiency
increase?
gets lower.
Well, but why do I want to increase efficiency? What does that do for us from the functioning of our radio? Longer battery life. That's right. You don't have to carry around one of those giant 20,000 milliamp hour power cells so that you can talk all day long or scroll TikTok. TikTok's more important. How many of you are active TikTok users? Good, good. You're too old. You're all too old.
How many is active Twitch users?
I don't even know what Twitch is, so I barely know what TikTok is.
YouTube.
Yeah, I got my. I'm a content creator. That's right. That's right. All right. So what else can we do to keep improving the power added efficiency of a PA? Well, we can start to change the bias point. So we're going to start to look at changing. Really, what we're going to be doing is changing the conduction angle. So in a Class A power amplifier, the DC power is high because no matter what I do, I'm drawing a constant amount of DC current in the device. So if I can do something to reduce the amount of DC current in the device, then I can reduce the DC power that's coming from the device. And indeed, that's what happens in a Class B amplifier. Now, you've probably all seen a Class B amplifier in your early electronics courses. Hopefully, at some point, you've seen a Class B amplifier. But you probably saw a resistively loaded Class B. We're going to load ours with an inductor, which just allows us to have the higher swing. So how do we conceptually? This is what a Class B amplifier looks like. I have some drain voltage, and ideally, my drain voltage is going to swing through some full range of voltage swing. But my drain current is not. It's going to do something like that. So it's going to conduct for half of the cycle, and then it's going to cut off for half of the cycle. And if I do that, then I find the DC component of a Fourier series of that particular wave, I'll find that the DC level went down compared to if I was doing a constantly conducting transistor. All right, so that's ultimately what we're going to do. We're going to reduce the conduction angle. So if we have a sine wave going through here, then we have a full 360 degrees of the sine wave. And in our case, for a Class B, we're going to cut the conduction angle down to half of that, 180 degrees. Yeah.
So do you just consider Class B to be 180 degrees and Class C anything below that? Like what's your...
No. In fact, we'll talk about Class C coming up, but there's a class. Yes, you're right, Peter. If you go below 180, then it's a Class C.
Okay.
Yeah.
So Class B is kind of arbitrary. It's just like the same as Class C, that it's exactly 180. Sometimes, like in audio, when people say Class B, they mean like push pull. So you have like two of them. So you actually have like 180.
Well, in a push pull, the only thing is that you're effectively getting a full signal swing. It's just that only one transistor is conducting current at a time. So the DC power consumption of each transistor is still lower.
Right. But here for us, for NRF, it's just Class B means 180 and Class C is less than that.
Yeah.
Like a circuit topology.
Well, and we will make push-pull Class B amplifiers as well. We're going to get to push-pull in just a few moments.
Okay.
Yeah, we can make push-pull Class A, push-pull Class B, push-pull Class AB, push-pull Class C. Class AB is a conduction angle that's somewhere between 180 degrees and 360 degrees. Yeah. All right. So no matter what happens, though, if we start to reduce the conduction angle, we start to improve the efficiency of the amplifier. All right, so the DC current is reduced by reducing conduction angle. And sometimes they call this the conduction angle theta, the Greek letter theta. All right, so our DC voltage, the average voltage is going to be equal to VDD. The transistor is biased through an inductor. The voltage is going to be allowed to swing at the drain all the way down to ground, and hence, in order to have an average voltage of VDD, it has to be able to swing up to 2 times VDD. So the DC voltage is equal to VDD because of that bias through the inductor. Okay, and ideally, we have this LC filter. In fact, it's a 4th order LC filter. We have 4 lossless passive components in our network. Each of those will add an order to the transfer function. And so we have a filter that is going to take any of the weird pulse shaping that's happening at the drain, that drain current, and it's going to provide a sinusoid at the output, ideally. Now I'm going to say more or less, because depending upon the quality factor of that matching network, how we actually design that matching network, this might not be a good filter. But ideally, it's going to cause a sinusoid at the load. Okay, so our DC current, if we go through and look at that, what's really a half rectified sine wave, we can find the DC value for a half rectified sine wave. In our case, it's going to be equal to 2 over pi times VDD divided by R opt. We already know that the DC value at the drain, VDC, is equal to VDD because of the short through the inductor. So our DC power is equal to 2 over pi times VDD squared over R opt. Now, our output power is still equal to whatever the output voltage waveform is, V out squared over 2 times R opt. So RMS voltage squared, ideally it's a sinusoid, and so RMS voltage squared divided by the optimum termination resistance that we present to the transistor. If we find the drain efficiency, it's equal to P out over PDC, and we can show that this is equal to pi over 4 times V out over VDD. And our max value here occurs for the maximum value of VDD, of V out, which will be equal to VDD. And it's pi over 4, which is equal to 78.5%, more or less. All right. Now, this is when we're talking about analog audio amplifiers, the class B is not necessarily a very good amplifier because it has a lot of distortion in the output wave. In particular, crossover distortion, where the transistor, if I'm doing a push-pull, one of the push-pull devices doesn't turn on, quite when the signal, gets up to the bias point. Takes a moment. It causes just a little bit of crossover distortion. And of course, that happens in our RF amplifiers as well, but this is still considered to be a linear power amplifier because as I increase the input power, the output power will increase linearly proportional to that input. There might be some distortion in the waveform that will be transferred to harmonics. So the waveform itself might be distorted. I might be transferring power to frequencies that I don't want them at, but more or less as I increase the power, it's going to increase the output power linearly by the same proportion. That's why they call this a linear power amplifier. But the drawback to this is in particular, as we start to increase the input power, the nonlinearities of the device are going to start to come into play, and I'm going to generate a lot of harmonic content just due to all that nonlinearity. And then even more than that, if I have a multi-tone signal like an OFDM signal, then I'm going to have intermodulation that's going to occur. So signals at different frequencies will interfere with one another and create third-order distortion that looks much like the IM3 problem that we saw in low noise amplifiers. So we have to, to worry about that. The main thing really, whenever you're looking at any type of RF course or analog course, is that life is full of trade-offs. How much distortion is acceptable? Well, there will be a specification for how much unintentional radiation you can radiate from your device. You have to make sure that you stay under that limit. And then, the people that are using your radio like to be able to demodulate their signals on the other end of the receiver and communicate with one another or listen to music or whatever they're doing. So these are how we, the things we have to deal with. Yes.
You said so. Did you say Class B is more susceptible to producing intramod than Class A?
Yeah, I mean the waveform. So just the drain waveform itself is full of harmonic content, right? And what we're ultimately relying on doing to get rid of that harmonic content is filtering it. And if we don't, we only have a fourth order filter to do that with. So if we aren't in this case, it might be less than fourth order. Probably only going to be allowed to use one inductor in practice. So it's going to limit the amount of filtering that we can do. But yeah, if I have a Class A amplifier, it's conducting the whole way through. The sine wave just looks like a sine wave, and ideally, now obviously that one will compress as well, but it generally will compress more gracefully than a nonlinear amplifier will.
Because you're saying like that comes from the Q term and
Well, I would be careful there. Like the Class A itself is, just in the definition, I'm defining it as an amplifier where I'm conducting for 360 degrees. In the Class B, I'm defining it as something that's only conducting for 180 degrees. So the drain current waveform in and of itself is nonlinear before I've done anything that causes it to compress. If I start driving the device harder, it's going, this waveform is not going to look like, this beautiful half rectified sine wave. It's going to start to distort. And as it starts to distort, it's just that there's more harmonic content there. Yeah. Now that's a hand wavy way of looking at it, but the less that waveform looks like a half rectified sine wave, the more other stuff I have in the waveform if I were to do a Fourier series expansion.
Yeah, but I mean, that would happen to the Class A as well, right?
Sure, it does. But, you have to think like the Class A's, I'm still getting 360 degrees of swing. So this can be qualitative. We'd have to drive the two into saturation. I would argue that most of the time, the distortion is going to look worse for the Class B amplifier, but you're right. It could. There are cases where I might drive it with the Class A with an impedance that causes it to be a disaster. Also.
Well, yeah, I'm specifically wondering about intramod, not necessarily harmonic distortion. But yeah, I'll look it up first.
Oh well, with respect to intermod, I mean the intermod. So what we really have here, the GM of the device. We measure the gain of the device as GM times R, right? Now the GM of this device, GM is defined as the change in drain current due to a change in input voltage, right? So no matter what happens here, my GM is going to be a much more nonlinear function than the class A amplifier will be. And so I expect that, and bear in mind, we might be talking about a Taylor series expansion, but really these are much more nonlinear circuits. And so oftentimes we have to talk about a Volterra series expansion, which includes memory effects. So we have big parasitic capacitances and inductors and things like that in the circuit that will cause the voltage and current to be held in memory for some period of time. And so if I do that expansion, I'm almost always going to find that the class B is worse.
Okay.
But that is hand wavy. I'll give you that. All right. So what can we do to reduce distortion or reduce nonlinearity? Well, we can do a couple of things. What do you think you can do as a circuit designer? Remember, you're not device designer, so you can't really change the transistor at all. What could you do as a circuit designer if you wanted to fix that distortion problem? There's one simple one and one a little bit harder. I would say that's the harder one to think about, but I'll grant you that. Okay, why does a differential circuit help us? So it's along the right lines. What I would say is that I have a push-pull circuit that is canceling my even order distortion terms to a first order. So the even order distortion terms that come to the drain of the transistor are in phase with one another, and so they're common mode canceled with one another. So the differential topology reduces even order distortion. Okay, what do you think maybe the easier is? Remember, we talked about other classes of amplifier.
Biasing up the transistor so it conducts greater than 80.
Yeah, so we can, I don't know if I said it, but VGS here, what would we make VGS equal to if we wanted the device to only conduct for half of the input cycle? I make VGS equal to VTH, the threshold voltage, yeah. All right, so if I make VGS greater than VTH, but still less than the bias that I would use for a class A amplifier. Well, this is where I have what we call the class AB amplifier. And really what we're doing with the class AB is just increasing the conduction angle. Now, I don't know if I would always say that the class AB reduces distortion because one of the problems when I start to operate in class AB is I do get some gain expansion. As I start to sweep the input power, the gain will tend to expand a little bit, so that can have some negative effects on the linearity. But generally, class AB amplifiers are considered to be more linear than class B amplifiers are. And it really kind of just depends upon how we're using them. All right, now, just like with any of the other technologies, we can still cascode. We can still do, with the differential topology, we can do class B or class AB. So all of the options are on the table. Yes, Rohit. Yeah, so what we mean by that is normally when we plot like AM to AM, so we might plot P in versus P out, or P out versus P in, or sorry, we might plot gain versus P in, and ideally our gain, we want it to look like that. A lot of times class AB amplifiers will look something like, they'll kind of have a weird hump and then they'll compress or whatever. So, and that's just happening because as I start to increase the input power, I'm moving the bias point around, and the bias and that change in bias point is causing the device to have more gain. Okay, so what do we do? Our differential PA might look something like this. So here I have a push-pull. I have one input transistor being driven by a positive going signal and one input transistor being driven by a negative going signal. These are just out of phase with one another. And they might come from a balun. And then I have, I didn't do it here, but I could, cascode these things. Now, the nice thing ultimately is when I do this, this differential mode operation, I have basically 2 half PAs. Each of these PAs can produce the same amount of power. When I add them together, I get 3 dBs more power just for using a differential PA for the same load resistance. But even more to the point, each of the transistors is going to provide the same voltage swing. So I can get 2 times the voltage swing at the output if if they're adding in phase with one another by using a balun. I should say here, or I get 2 times the voltage swing, and each of the devices only has to carry half of the current. So I have twice the voltage and half the current. That means that the impedance, the R opt of a differential PA is 4 times the R opt of a single-ended PA if I want to deliver the same amount of output power. And that's maybe the biggest advantage that you get in using a differential circuit. So we clean up our harmonics, we do all those kinds of things, but we also get to work into a much higher impedance, which means I'm going to have less of an impedance transformation that I have to make to deliver the same amount of power. And I'm going to have less, so that means less loss in the matching network. And less current division as well, because the R opt is bigger, so I'm not burning as much in the current division with the output of the device. All right. Now we have a couple of drawbacks to our differential circuits. Layout has to be very symmetric. Remember, one of the reasons that we're doing this is to cancel even order distortion. If the layout isn't symmetric, then that means that we're not going to do that perfectly. We're not going to have a perfectly common mode even order distortion tones at the 2 output sides of the differential pair. So I'm not going to get perfect cancellation. So that's one problem. And maybe the biggest drawback, or at least it used to be the biggest drawback, is that you have to convert from differential-ended to single-ended, because almost every antenna that you're practically going to drive is going to be a single-ended antenna, at least on a modern cell phone system. It's very rare to see a dipole any longer. Most of the time you see some type of patch antenna, single-ended patch antenna, and that means you're going to have to do a differential to single-ended conversion. This used to be a big deal, but nowadays the tools, almost all of your PDKs provide balins naturally, and the tools are also very integrated and fast to do simulations of balins. So we can do balins a couple different ways. One of the ways is, of course, with a transformer. So I might do something like that. And one other thing that we can do is called a polyphase filter, or sometimes they call it an LC balun. And basically the way that this circuit works is we do a plus 90-degree phase shift in one direction and a minus 90-degree phase shift in the other direction. So in other words, we have a high pass filter in one direction and a low pass filter in the other direction. And we can make a balun. We're going to ground the tap there. Here's our plus signal, our minus signal. And our center frequency here is equal to 1 over root LC. And if we want to do any impedance transformation, we can make the characteristic impedance of this balun equal to square root of L over C. So this is called a polyphase or LC balun. All right. All right. Any questions? So on Wednesday, we're going to look at we're going to start looking at class C, and then we're going to start looking at switching amplifiers, which are not amplifiers at all. Yeah.
So for this differential one that we showed on the previous page, did you call that a push pull?
It's a push pull, yeah.
So like, in audio, which is where I first learned this, like push pull means that there's like a 360, basically, like say first one's pushing and then like the others like.
Yeah, so if I did this with a class B amplifier, it's doing the same thing. But really what we mean by this is that, you know, when I have a positive going voltage on M1, it's going to cause current to go in this direction.
Yeah.
And of course that would mean that I have a negative going voltage in that direction, so current is going to go in that direction. So it's pushing current into one side of the circuit and pulling current from the other side of the circuit.
Okay, but then what about when the other half of the sign?
Yeah, same. So same. No. Well, if I bias it as a class B amplifier, yeah, I can do it. Yeah.
The other angle.
Yeah, I'm not playing here. I'm just looking at class A, but yeah, we could do a class B amplifier here. It's still a push pull. I'm still, if I look at the harmonic content and the voltage waveforms, I'm still doing more or less the same thing. But you're right, it's not practically operating in the same way. But I would still say I'm driving one half of the circuit and not driving the other half of the circuit in that case. Yeah. Yeah.
So you basically said the reason that we have unit cancellations because we have in-phase signals that all in that takes the common mode away. For the aura, would we not have out-of-phase contributions and add that up?
Yes. So the odd order contributions are going to be they're differential. So we're not doing anything to cancel the odd order harmonics. Not practically, no. But we're not doing anything to help them either. So Peter, the way to think about this is that one of these devices is always going to be conducting. in a Class B mode. When I swing above V threshold on one device, I'm naturally swinging below it on the other device. So that's going to cut the one device off, but it's going to turn the other one on, and vice versa.
Okay, okay.
Yeah.
But does that mean that you don't have any of that drain from the protective below? The drain current is like continuous now, right? Or sorry, but like there's none of that like.
Well, each device itself is still cutting off, right?
Yeah, but from below, like the load sees like a.
Well, I've got, I definitely don't have like a pure sine wave being driven of current being driven into the load any longer. In fact, each side is being driven with a half rectified sine wave that's 180 degrees out of phase. So the load current is like doing this and then doing this. So these are 180 degrees out of phase. Yeah.
That result in a small portion of time in this more current.
Yes, and that's why that's where we have a Class B amplifier. We'd have crossover distortion. And if we want to get rid of that, we can increase the threshold or the gate bias a little bit to cause it to conduct for a little bit more time. Yeah. Okay, before we go, I wanted to maybe see if I can open up Cadence and show you one or two things. So I did load a video onto Canvas. So we're having a few issues with the inductors in the kit. For some reason, the CDFs, the equations that basically underlie how you derive the inductance from the physical geometry, are not getting triggered. I'm going to see if I can download a new PDK. We are in the middle of renegotiating. In fact, it should be done, I hope, but I haven't checked in a couple of days, our Global Foundries agreement. If that is the case, then we will then that will be fixed. If not, we will have to find a workaround. One workaround is we do have the newest version of EMX, which technically has its own built-in geometry designer, so it can design passive components by itself. I haven't played around with that too much, but I'll see if I can get that working. And then one other thing I'll try, and whoops, get some of you have simulations where you might want to show what the transconductance of a device is as you sweep the width of the device. We're going to set that up like we would any other simulation. We'll set width as a variable. We'll sweep width, and then if we run a DC simulation, there is a way that you can, with the calculator, grab the individual parameters of the transistor. I do have a video where I show doing this for different capacitances, but we can do this for transconductance, threshold voltage, whatever. And I think we're going to run out of time today, so I'll try and get a video posted in the next day or two that shows you how to do that if you're struggling on your projects. You don't need that for your homework. All right. Oh, it just, no, we're still on.
Yeah, we still got 3 minutes.
Oh, no, it finally loaded. Okay. I am also aware that the clusters are slow. I won't penalize you for it. I'm working to find an alternative solution, but I would do this on ARC, but on ARC, I have a very hard time controlling permissions for files because I don't have sudo on ARC. I do have sudo on our clusters. So if we continue to have problems, I will find some way to make it more feasible. Just bear with me while I figure out how to do that. I won't pull a 4220 from last semester. We will find something before then.
Your help's
right.
definitely appreciated there. Thank you.
All right. Well, I did a lot of the CAD setup for that class as well, but that was the clusters are just what they are.
Yeah,
We're replacing them.
Just base build up like at the last like day of the class.
Yeah, we are in the process of replacing them. So, okay, I will not physically be in this classroom on Wednesday. Hopefully, this will be my last trip of the semester. I'm going to go Mac Tech, which ideally was to lobby defense department program managers for money, but none of them are allowed to travel. So I don't know who I'm going to be lobbying for money, but I'll ask somebody for money.
I think new clusters.
I'll ask them for clusters. Yeah, exactly. All right. So from Wednesday, we will have class. It will just be virtual. Hopefully the last virtual class of the semester. And see you then.